My name is Alex. I work at Akamai as a principal engineer for the platform group. In a previous life, I was the CTO of Concord.io, which was a distributed stream processor written in C++. It was acquired last year by Akamai. My talk is about how to build the fastest RPC framework in the West. So with Seastar, which is the foundation technology of Scylla, I was able to achieve double-digit microseconds on the tail latency to communicate between two remote computers. Cool. All right, for the guys that are coming in, this is a talk about Smurf. That said, it's just the name I picked. It has no vowels. So, okay, let's start. My name is Alex. I work at Akamai. I'm part of the platform group. And there I'm working on an IoT initiative, so that's what I'm working on now. Prior to that, I was the founder and CTO of a distributed stream processing engine. It was called Concord.io. It was acquired by Akamai earlier last year, yeah. And it was also written in C++. It's sort of, at the time, there was also all of the stream processors were written in Java as well, and we wanted predictability and performance, isolation, multi-tenancy, supervision, failure recovery. And so I decided to write it in C++. I also worked at NetTech, but that's boring. So I want to talk to you guys about Smurf. But first, I want to give you a little bit of the background as to the reason of this framework. When I was at Concord, what users wanted to do is they wanted to do exactly once stream processing. That's what they wanted to do. And at the time that I was testing all of the open source queues, written in many managed language, so tons of VMs like Erlang or the JVM and so on, none of them could keep up with the traffic that we were pushing onto these queues. All of the databases that we tested crashed. All of the queues crashed. And those that didn't manage to crash were either too expensive to run or the tail latencies were just too high. So there was nothing there. And to be clear, what I wanted is a low latency queue that was also high throughput, relatively speaking. What you can think of it is, can you design a queue that is 2-digit tail latency that is sending millions of requests per second or a batch size of, say, 1024 messages. When I benchmarked then, the fastest open source queue at the P90th percentile, which who measures that anyways, is 150 milliseconds. At that point, it's no longer real time. I mean, it's kind of real time, but not really. And at the tail latency is 2 seconds, which means that the SLA that the software can do on top of the stream processor could be at best 2 seconds. So during my tenure at Concord, we posted a blog post on this too back then, but we were trying to test Spark and Kafka, and sometimes we would hit this 4-second JVM pause, and we're like, I don't know, no clue why it would just halt. So we weren't doing any particularly interesting. We're just adding integers at that point. So can we do better? Of course we can do better. That's why I'm here. Otherwise, why would I be here? This is the most important slide of the talk. You can go to sleep, but if you do, I'll see you at the exit. It is, in particular, this is the per node overhead of the RPC. And many things to know, but the first one is the flat tail latency, I think. So if you go all the way up to the P99th percentile, the overhead of parsing the data off of the wire, serializing the RPC, executing a set of filters, dispatching the method, executing a set of outgoing filters, reserializing the type, and flushing those bytes as a serialized type onto the wire is 8 microseconds. The slowest request that I benchmarked at, I think 32 million requests was this particular benchmark, both DPDK client and server, it was 26 microseconds. And That's what it is. Again, just to kind of highlight what this per node overhead is. So this would be the overhead of a server software that you would write. Right? So you would read the socket, parse the RPC, dispatch it, and flush the bytes at a p99th percentile of 8 microseconds. I'm introducing the SMF. In particular, I'm going to introduce the SMF RPC, and I'm going to use the term interchangeably. SMF is actually a collection of distributed system libraries, but for this talk, I'm going to use them interchangeably. So if I say SMF, I mean the SMF RPC. So what is it? It is a new RPC framework. You can think of it like gRPC or Thrift or Cap and Proto, but for microsecond tail latencies. It is built on top of the Seastar future and I/O work that these guys at Scylla have worked on and built on for a while. What I started this with is actually started this as a way to understand Seastar in the beginning too, and I sort of I wanted to use a framework that allowed me to write software that would scale linearly with the number of cores. And Seastar sort of fit the perfect bill at the time. And I also wanted a cross-language serialization format. So I didn't want to write something just for C++, because in the real world, you have clients in Python and mostly Java. That's what people write web apps in. So I wanted a cross-language serialization format. I wanted a serialization that was fast, and basically you get zero-cost serialization with flood buffers. And I wanted it to be small. HTTP is slow, and it's large, and it's text, and who wants to do that anyways? So I just extended the flood buffers IDL-compiler to generate the code. So let's walk from the top as though you were a user of this system, and I'll explain the internals of the system as I go through. If I'm going through the slides really fast, tell me to stop or slow down or something. I'll try to go through them relatively fast. So a table is a C struct or a Java class, Python class, and so on. A namespace is a namespace. In this example, the useful thing to note is the RPC service IDL definition. And so the Google flood buffers schema parses this file, call it service.fbs, and it gives you a type that you can manipulate in code. And so I take this type to generate a service called SMF storage. And so I'll generate stubs for the server and the client. In some RPC implementations, they just generate the server, and you're like, okay, well, I have a server, but how am I going to communicate between nodes? And so you kind of get stuck there. So I generate both the server and the client. The only method in the SMF storage is called get. It takes an input type called request, and it returns a response. You would, there's a little command line util that you say generate the file name, and that's it. It's very easy. So it's not a demo because I didn't bring my Linux laptop from Europe. So let's talk about the RPC client, how you would use it on your code. So first, you define a request type. This is what you're going to send to the server side like you would with any RPC framework. And notice that this just looks like regular C++, right? There's no socket. There's no open anything. It's all code generated for you. Each client comes with a non-thread safe shared putter. So if you look at the Seastar shared putter implementation, they don't use atomics. In fact, most of the Seastar code base doesn't have atomics. And so this is explicitly non-thread safe. This uses basically a polymorphic type shared putter as opposed to the lightweight shared putter, but that's implementation detail. And so you just call the method client get, and that returns a future that you can chain in the regular continuation chain that you do with normal Seastar code. On the server side, you extend the class. So this is code generated. You define the method, and it returns. Notice that it returns a Seastar future. I'm not sure how to do the pointer. No, it doesn't come with it. There is no pointer. Got it. So it says virtual Seastar future, so it always returns Seastar future, which means you can chain them, you can manipulate them on regular Seastar futures. And so that's about it. This framework was heavily inspired by Twitter Finagle or Facebook Wangle, which enhance or sort of extend the notion of an RPC. So if you use Thrift, for example, okay, you code-generate a Thrift IDL, and it gives you a class and a method, and that's about it. But oftentimes, you want to put in a set of filters, like a pluggable decompression strategy, or maybe a by-throttling filter, or an authentication mechanism, or something right before it hits the method in a way that is generic. Similarly, for a set of outgoing filters. And of course, you dispatch the thing that is actually going to do work. A filter is nothing more than a T, return a continuation of that T. So I'll give you an example of how to build a compression filter. It's very easy to build a compression filter. Here, you're taking a filter of an envelope. An envelope is the untyped API. So this comes with two levels of API, right? One is the untyped, which is what I write, and most users will deal with the typed API, like you take a person and you return a person if that's what you want to use. But at the low level, sometimes you're going to turn that type and serialize it into a set of bytes that you're going to eventually flush onto the wire. Here, we're going to build a Z-standard compression filter that says if the size, the data that I'm sending down on the wire is greater than some threshold, I'm going to compress it. Relatively straightforward. So how do you use it in your code? On the client side, you said add it to the stuff that I'm sending to the server. And similarly, on the server side, you said add it to all of the stuff that I'm sending back onto the client. The RPC that invoke all is pretty standard tooling of how to do Seastar cross-shard operation. There is a super type called the sharded type, which effectively takes any subtype that conforms to an API that allows you to perform methods on that type, right? So this says on all the cores that are running on this server, register an outgoing filter, which is the Z-standard filter, with a threshold of 1,000 bytes. It comes with a batching API. So I think Pavel added the SCADA, which is effectively a way of trading latency for throughput. So all of these filters execute in batch. Typically, most of these filters are for compression, data manipulation, rejecting requests. I saw about a 10% improvement on the latency with a few requests, but I actually don't have data on that. Now let's talk about the request anatomy and how do we make it cross-language compatible. First, this thing is small, it's 16 bytes. And I want to talk about this macros. So what this macros do is it turns off the padding by the compiler. What does that mean? When you access fields on any class or struct, the access will always be in word size. That's how the hardware works, right? It'll access a word size worth of data. And if your data is shorter than that, it's either padded or the compiler has to generate extra instructions for half word size to actually get access to the bits that are important to that field. And so what this macro does is it turns off the padding by the compiler. That means that the flat buffer's IDL-compiler has to pad each subfield. And then at the end, it has to make sure that the struct is also padded aligned to effectively word size. It also happens to improve your cache line coherency and prevents all sorts of other issues in regards to concurrency. We're not too stressed about that because Seastar doesn't share data across multiple cores. There's no atomics. There are no locks. What this does do is that it enforces a layout of little endian architecture. Big endian architecture have to pay the cost of translating the bytes. In most operating system and in most CPU architectures, there will be a zero-cost API. The next thing is I want to talk a little bit about this bit flag. So compression right now, it supports the Z standard compression and LZ4. LZ4 is super fast. I highly recommend it. And Z standard gives you really good compression. It's pluggable. These bit flags are just internally. I support headers, or the project supports headers, in the same way that an HTTP header works. So for lots of requests, you want to tag whether, let's say that you're tracing your requests across a set of computers, and you want to see the causality or the chain of requests that caused that. Well, this bit flag says, oh, instead of just reading the payload, read a little more metadata so that you can parse the headers. The session is actually the request ID. So what the SMF RPC framework does is that when you send data to a server, it actually internally stores a promise, which is sort of the stuff that will get fulfilled when the data comes back from the wire. And it'll, for all intents and purposes, will suspend that continuation until data is available on the wire. The size is the size. The checksum makes sure that the data is not corrupted over the wire. So this is pretty rich. And XX hash 32 is super fast. I actually took that from the LZ4 compression. Meta is on the server side, the ID of the function that will get dispatched on the server. And on the client side, it's used often as sort of HTTP status code. If you look at most APIs, whether it's for databases or any system, you usually have a status that is coupled with a payload, and the payload could be different. So I need to move a little faster. So how does this work? The code gen, assume that there is a function that gives you the fully qualified name, which means the namespace, the fully resolved namespace type. For the service ID, I take the hash of the fully resolved service type. For the method ID, I sum all of the types, and the sum is the function of concatenation. So I sum of all of the fully qualified input types, all of the fully qualified output types, the name of the method, and a separator to make sure that there are no collisions, and I XOR them, and that's the dispatch ID. So on the client side, there is this number I want you to pay attention here, is the 1711955 number. That's the method ID that just happens to be the hash of what I just said, which is the hash of the request, response, and get in a fully qualified version of that. On the server side, okay, I take the same method ID and I XOR it. That's how the dispatch works. The alternative, instead of having a one-table lookup, you would have two-table lookups. So one for the service, because you can register an unbounded number of services with each running server, which is actually listened to TCP sockets. So the alternative is you either have one lookup to get the service ID and then the method that you're going to dispatch, or you XOR them and you do one lookup. This is just sort of the service that the interface that is actually what the service overrides. This is very similar to gRPC. If you look at the source code of gRPC, it's almost the same. I took a lot of the ideas from the way they did things. Service names just allows you to pretty print any service. Methods also come with a pretty printing version so that you know exactly what's running on the server. SMF, the RPC framework, in fact, all of the libraries underneath it come with built-in telemetry. But the telemetry that matters for RPC is the latency distribution. And not just the P50th and P90th, but actually 100% of the distribution. HDR histogram was I think Giltin invented at Azul Systems, maybe Cliff Click, I don't know. This gives you 185 kilobyte in-memory footprint for being able to record n number of requests at a microsecond interval for up to an hour. So it sort of gives you pretty good room for that. On the client side is optional. You just say enable histogram metrics is disabled by default. On the server side, it's enabled by default because I want to understand the performance of the server, in particular the latency distribution. Zach just talked about Prometheus. All of the SMF projects, sub-projects, and the RPC as well, it extends the Prometheus API. So if you have Grafana, it just sort of gets picked up, and you have to do no work to get that. So what about performance? This is it, right? So I said in the beginning of my talk that this is the most important slide. This is the performance that you should expect. With a DPD client and a DPD server, you should get 8 microseconds tail latency on that. And at worst, the slowest request is 26 microseconds. But let's dig a little deeper into what that means. End-to-end, which is what the user will see, right? So if I'm a user and I'm a DPDK-enabled user, I will see these tail distributions, right? So this is what the user will experience. However, if you take the connection, so the first request, which sort of establishes the TCP connection and so on, the slowest request end-to-end at 32 million requests, doing about 1.5 million requests per second, was 151 microseconds. And I think that the work that we did with the SMF is to have a relatively flat tail, right? Like this sort of makes sense. That little curve that you see that I can't point to, but you sort of see when it grows up, is that SMF comes with built-in throttling. So Seastar and Nadav wrote a really good piece about it. You have to use semaphore to sort of hold the speed at which Seastar is executing things. Otherwise, you're going to run out of resources. That curve is when you start to run out of memory on a per core, and sort of things balance out. Regardless, it's a pretty flat tail, in my opinion. Okay. So some future work. I want to leave a few minutes for questions, but I want to show you some what this powers. I think this is a useful thing. So this is a cool RPC framework. To talk about the future work is I hit a TCP bug that it was difficult to debug. It could be my lab setup. I haven't had a chance to dig too deep into it, but there was a windowing stuff that only happened after a few million requests per second we're handling and 36,000 requests by a single server. So I was trying to saturate the server, playing around with that, and I got to 1.5 million requests per second, but it also was exhibited by the CREC and HTTP pair programs that Seastar comes with. I want to add a JVM, Python, and Go code generators. They're pretty easy now that the framework is there. And in the last minutes, I want to show you guys what this powers. So I am writing a write ahead log, which is powered by this RPC framework. This is a benchmark that shows the speed up of using Seastar and SMF in comparison with Kafka.
What's the IOPS rate for the?
As in like the operating system IOPS?
No, I mean, how many ops a second are you pushing to get the latency? This was measured at.
Okay, good. So I was doing. It varies between Kafka and that. I was trying to push 3 million requests. I finished it at the tail latency in 54 milliseconds, which gives you about 2.2 million requests per second. Each request was, okay, so I have to give you details of how Kafka works to explain this. Kafka works in batches. So Kafka sends batches right? But it counts the QPS as individually. It doesn't count per batch. The number of batches sent to the server were about 122 batches. Each batch was 8,196 messages within each batch. Each message was about 100 bytes per message within the 8196 bytes. Kafka's throughput per producer was about 500,000 requests per second. On a single producer, a SMF could do 1.7 million requests per second if I measured in the exact same way that Kafka does. The main thing to note, which I was alluding to in the tail latency part, is that this is relatively flat. Here, this shows it better, okay? At the 100th percentile latency, it just basically goes a little bit and stays the same. It doesn't really spike, right? I mean, I think the difference is almost not even comparable at this point, but it's 41 times faster. And the QPS is about 4, a little bit less than 4, like 3.7 if you were to measure it what Kafka did. I have more details on the website. I just wanted to show you that at first I built a product to use the RPC because I didn't want to build an RPC that was cool and fast that didn't have any application. I wanted to build an app that used the RPC to make sure that it worked. And that said, I have 1 minute and 40 seconds in case people have questions about any part of it. I'll go back to this in case you guys want to check out the GitHub.